Okay.
There you go. 10 minutes.
All right. Here we go.
Okay, so the problem that I want to discuss tonight is when you finally have a customer and they ask you to provide a prototype for 3 use cases in the telco domain. So that was real-time location-based offerings, network congestion monitoring, and cell tower anomaly detection. And then the following conversation ensues. So can we log into your network? Answer is no. Can we get your data? Answer is no. Anonymized data? No, but can you help us? And that's the trouble with real data. You cannot share them because they're confidential. And anonymization, when you correlate it with other data sources, well, you can always de-anonymize it. You look at the New York Cap data set and the de-anonymization of the Netflix price data set. Sometimes you cannot get it because it's too big, it's wrong scale, it's out of date, it's out of sync. It's technically difficult to get at, or most data hopefully do not contain anomalies, and that's sometimes the use case you want to investigate. Also, you cannot break reality. You cannot invoke disaster for the sole purpose of obtaining data. And in many cases, you do not understand it because you don't know the history and you lack the domain knowledge. So what you do in that case, there's a smart guy from MopR, Ted Dunning, who wrote a book sharing big data safely. And he said matching performance indicators, KPIs, is better than matching data details when generating fake data, which means when the KPIs match well enough for fake data versus real data, the fake data can then be used for experimenting with process of interest, which is in this case learning machine models or tuning machine learning models. So for this project, the KPIs were pretty straightforward. I will not go over them individually, but they're embedded in the rest of the discussion. So with that out of the way, we can start thinking about building a solution pipeline. We do not have real data, but we have the KPIs that indirectly define the nature and behavior of simulated data, so we can build a simulator. It provides data streams to a bus, in this case Kafka. But in reality, for telco data, you will have to build decoders and custom serializers to translate that into JSON or whatever. Spark is the computation engine and consumes the data streams. And then some streams need persistence because they are long-living streams. They outlive the size of a sliding window. So yeah, for those, we just persist them in Cassandra. The results of the computations by Spark are published again on Kafka. And then a Node.js server consumes the computed streams and publishes them via WebSockets to the browser. And visualization is done by D3. Okay, in this case here we had probes that provided 2 types of streams. We had attached streams, which are long-living streams, meaning they only occur once when a subscriber connects to the network, but they do contain vital information like for identification of the subscriber, for example the IMSI, and it also contains a better ID for correlation with other streams. And then we had context streams, which are fast, short-living data streams. These events occur multiple times during a period the subscriber is connected to a cell tower, so multiple times per second even. There's no subscriber information, only the bearer ID. It does contain cell tower information and location, and it contains metrics, and in this case these are controlled by templates of the simulator. So that brings me to the simulator itself. This is built in Scala using the Akka toolbox. It's horizontally scalable, and it can be deployed as a cluster spanning multiple machines. The simulations can be triggered through the UI or also through REST. Now, for big simulations, it's better to invoke that through REST because the user interface will not be able to cope with the locations that are being pushed back through WebSockets. So we have three types of actors. There's the simulator itself, which is it's a mock of the universe, so it's a singleton. It controls the space dimension and in the sense that the field is defined by the cell towers for a given MCC, that's mobile country code and mobile network code, MNC. Then it also controls the time. So it sends ticks into this universe, and also it controls the velocity at which the subscribers travel through the field. And then there's then we have cell towers, which are a different type of actors. So there's multiple of those. These get their information also from OpenCellID. So that's the database that provides the MNC, the MCC, the latitude and longitude of the cell towers. And then we have subscribers which get a fake identity, random identity with name, IMSI, and corresponding to the MCC and NNC. So that's the three types of actors. Then it brings me to the first use case, which is real-time location-based offerings. So this user interface allows CRUD of the geofences. And the Spark event processor reads the persisted geofences every so often. That's in this case is every 5 seconds. Spark correlates the two streams to identify the subscriber and the location. And then when a subscriber connects to a cell tower that is inside one of the geofences, a message will be created on the topic in Kafka. And that can then be used for location-based offerings by sending an SMS with an offer or something, for example. I mean, this is a very crude way of communication. I mean, if you don't know the routines of a subscriber, this could lead to a worse kind of spam, in fact. So there's something missing there. The next use case is network congestion monitoring. So for every metric produced by the simulators, moving summary statistics are calculated, also in a configurable sliding window. So that's just the average count, standard deviation, maximum and minimum. These are published on topics in Kafka, and they can also be used for generating heat maps or triggering alerts or something like that. Then we get to the last use case, which is network anomaly detection. So a typical way for doing this is using k-means clustering. You determine to which cluster each of the data points belongs, and then you measure the distance between the data point and the centroid of the cluster. So data point is flagged as an outlier when the distance exceeds the dynamic or static threshold. The data points could be multidimensional, but for visualization, this is only 2 dimensions here. So we use 2 metrics, which is round trip time and byte loss in this case. If you want to use higher orders, if you want to use more dimensions, then you will need dimensionality reduction.
Nog 1 minuut, Koen.
Yep, but I'm done. So, and as a summary, so if you can't get the data, you can fake them, taking the KPIs into account, and simulation is great for injecting anomalies, playing with machine learning algorithms, and control over this universe. So.